Welcome to Jared Wozny's design module lesson on screening systems for wastewater treatment. This presentation will cover the basic information about screening systems and standard design criteria and equations used in sizing screening equipment. We will run through a step-by-step example of designing a screen for a treatment plant and conclude with a description of current manufacturers of screening products. This design module focuses on screening, which is a preliminary treatment of wastewater found in most wastewater treatment plants. Screening is usually one of the first unit operations found in the liquid treatment train. Its purpose is to physically remove large solids suspended and floating in incoming wastewater streams. This is to prevent clogging of equipment farther down the liquid treatment train. A screening system is usually set up with large bar racks or trash racks that are followed by smaller bar screens. We will now look at standard design criteria. The table illustrates common criteria for designing bar screens. The major parameters involved in design are the width and depth of bar screens, which are 5 to 15 mm and 25 to 38 mm respectively, the openings between bars from 15 to 75 mm, a slope from the vertical less than 30 degrees, an approach velocity around 0.6 to 1 meters per second, and allowable head loss from 150 to 600 mm. A manually cleaned bar screen is usually designed for a smaller velocity and smaller bar dimensions. A typical head loss through a mechanically cleaned bar screen is 6 inches or 150 millimeters of water, which we will reference again during the step-by-step example. There are several equations to consider when designing screening systems, but the most important equation to use is the head loss equation. This equation determines the head loss using the velocity through the bar screens, V sub bs, the velocity approaching the screens, V sub a coefficient factor, C, and the acceleration due to gravity. This coefficient factor is 0.7 for clean screens and 0.6 for clogged screens. A similar equation is used to determine the head loss for a fine screen. This equation includes the discharge or flow rate through the screen Q, the effective open area A, the discharge coefficient C, and gravity G. Since an important parameter for selecting an effective screening system is head loss, the following step-by-step example will determine the head loss through a mechanical bar screen. If the calculated head loss is higher or lower than the allowable range, then the screen will need to be redesigned for newly sized openings and bars. This mechanical bar screen is designed to have 15 mm openings and 15 mm bars. It is installed to a rectangular channel and the approach velocity cannot exceed 0.76 meters per second as noted by Wiesmann. The first step is to determine the net area of the openings in the bar screen using variables W and D as terms for width and depth. The cross-sectional area is multiplied to a ratio of the opening width and the sum of the opening and bar widths. The resulting net area is 0.769 times the width and the depth. Using the continuity equation, we can equate the velocity and the area of the approach channel to the velocity and area through the openings in the bar screen. Rearranging the equation to solve for the velocity through the bar screen openings, the resulting velocity is 0.988 meters per second, which is and should be larger than the 0.76 meters per second in the approach velocity. Using the head loss equation, the estimated head loss through the bar screen is computed as 0.029 meters. This isn't a great loss in energy or a drop in pressure, considering that a typical head loss is around 0.15 meters or 6 inches. A second step-by-step example focuses on calculating an area for a fine screen system. Two fine screens are operated in parallel to treat 2,000 cubic meters per day entering a wastewater treatment plant, and the maximum head loss allowed through each screen is 1 meter. Assuming the screens are clean, we need to calculate the effective submerged area of each screen. First, we divide our total flow rate by 2 to account for the parallel treatment trains. This gives us 1,000 cubic meters entering each screen. Our next step is to rearrange the head loss equation for fine screens to solve for the effective area. The new equation still accounts for a discharge coefficient, which is 0.6 for clean screens, and the acceleration due to gravity. Using this rearranged equation, we calculate a necessary effective area of 291 square meters. This value is really high, so more screens could be implemented to reduce the effective area of each screen. The following are just a few major manufacturers of screening equipment and other unit operations products for wastewater treatment. Some manufacturers, such as Headworks, are noted for having very tough screens that are built to withstand extreme conditions. Another manufacturer, Franklin Miller, boasts of having innovative screen designs and works with new installation and upgrades. Their line of spiral lift screens have been designed to meet different needs, from fine screening for heavy prison water to screening for treating septic streams. Here is a list of references used to help compile the contents taught in this design module. I hope that after this presentation you will be more confident in your understanding about the purpose and design of screens in wastewater treatment. The design criteria and equations are standard methods for sizing screens for treatment plants, and current manufacturers of screening equipment are helpful in selling you a product that will cater to your specific needs. Good luck and happy designing!